Hi, I'm Zhexin Shen. I'm from Machine Learning Group 36. Our final report is about some popularity predictions. Our group members include Yue Song, Morgan, Jingzhi, and Austin. Music has played an important role in our lives. It helps to reduce the stress of daily routine and inspire us when we are feeling down. Nowadays, more and more people enjoy music in daily basis. The music industry is always looking for the next big hit song, and all the musicians are trying their best to make their work listed as one of the most popular songs. Therefore, a machine learning model that can predict the popularity of a song could really make a difference. Presently, we would like to use the dataset from Kaggle, which consisted around 13,000 sets of data. The dataset has 15 features of each sound like energy, key, tempo, and so on. These data are collected from Spotify API, and the song popularity value is included based on factors such as save rate, the number of playlists, skip rate, and so on. The goal of this project is to predict the popularity value based on these kind of features given. A thing also I would like to add is about we cannot due to the time is limited and the feature extraction costs so long and so complex things to do. So our training and the test data are limited to this kind of sound, but the sound dataset is quite enough for the different kind of training. The first method we used is the unsupervised learning with the principal component analysis. This helps us discard the least influential parameters in this kind of features. First, we do the data visualization with the histogram. As you can see below, all the map looks good, but the instrumentalness is kind of a weird plot. However, we still decide to keep this kind of feature because the instrumentalness is actually intuitively an important structure for our training. And we also to determine the features are individual to each other, so we plot a correlation net. This seems fine, just the loudness and the energy are strongly correlated, but we still decide to keep those two features because the loudness is actually an important feature which will be shown in the next section. The first simplest supervised learning model is the linear regression model. For this work, we have implemented ordinary least squares ridge regression, which use L2 regularization in the loss function, lasso regression, which use L1 regularization in the loss function, and elastic net regression, which use both. For ridge regression, the lambda value for the regularization is determined via crossed validation used the leave one out method, and for lasso and elastic net regression, the lambda value for regularization is iteratively adjusted along the regularization path. Given the categorical variable in the original data, two separable methods were used to handle this, using one-hot encoded data and discarding the categorical data and only regressing on the continuous data. For each method, two scaling methods were used on the continuous data. Standard scaling, where the data is adjusted to zero means and unit variance, and min-max scaling, where the data is adjusted to fit a specific range, which was 0 to 1 for this work. The results for each four data group are shown below. The computation for the one-hot encoded data were performed on data that was transformed by PCA and related to 21 components, while the continuous dataset work was done on just 10 continuous variables. The matrix for determining the success regression method were the mean MSE of the regressions, the R2 of the linear fit, and the classification matrix for whether the predicted y value was heated or not, where heated is defined as a y value greater than the mean y value. Another regression algorithm we choose is supported vector machine. Normally, the SVM is used for classification problem with kernel trick and soft margin. SVM can give a clear margin of separation between classes efficiently. Actually, SVM can also be used for regression problem. The corresponding algorithm is called supported vector regression. The object of SVR is to basically try to have a maximum number of components that are within the decision boundary lines. And the best fit line is the corresponding helper line, which is the center of the data decision boundary lines. The margin between hyperplane and the decision boundary is a parameter called epsilon that is defined by the users. After parameters turning, the prediction result of SVR is shown below with corresponding mean square error and mean absolute error included. It works slightly better than the linear regression but has not really made a big improvement. The final supervised method that we implemented was a neural network. A neural network which takes an input of a size and performing weighted combination of features through layers with nonlinear activation between each layer to give an output of size n minus plus p. For our specific regression cases, we use certain features and a one-dimensional regression target. Since three of the input features are categorical variables, after performing one hot encoding, we have the input and output. We implemented the neural network with a general architecture of fully connected layer with a leaky ReLU activation between them. In order to specify the hyperparameters of the network, we initially attempted to manually train them. Ultimately, we found much better success following the use of automated hyperparameter searching using the Optima framework, which uses efficiently sampling methods like TPE and CMAES to search over the search spaces for optimal hyperparameters. For our work, we use these to optimize the flowing. Using L1 loss for 80-20 training testing split over the dataset, the learning result curves are shown below. The optimal results from the best epoch during training are mean absolute error is 15.19 and classification accuracy is about 60%. The final output of the neural network predictions are shown below. For all the methods we tested, the best performance we have is from SVR, which gained 60% accuracy. The main reason we suspect for the poor result for the neural network is that the size of the dataset might be too small for the network to learn the relationship between the features and the result. The network structure and the hyperparameter could be likely be turned to improve performance. And that's all we done for our project. Thank you for listening.